Yeah, thank you very much, Michael. And first of all, before starting the presentation, I really want to deeply thank the organizer for giving me the opportunity to be there today and to attend this really great conference. Today, I will talk to you about the emergence of oscillations during fluid injection in water-saturated sands. And this is based on the work of two PhD students, Jérémy Vesser and Shaima Alaoui, in collaboration with colleagues from my laboratory, Sylvain Joubeau, Michael Bourgoin, Romain Volk, and also in collaboration with another physicist colleague, Germán Varas, from the University of Valparaíso in Chile. And finally, it's a very close collaboration with Aurélien Guier, who is a geologist in Geosciences Montpellier in the south of France. Before starting, let me tell you about our geophysical motivations, which are twofold. The first one is fluid seepage at the seafloor, and the second one is soil erodibility. I will get a bit more into the details right after. But you will see that based on this geophysical motivation, we start a physics experiment which led to a very nice observation of oscillation of particle-laden jets. Our main motivation at the beginning was fluid seepage at the seafloor. You can see a beautiful picture here of a diver in Panarea Island in Italy. And you can see that this diver is surrounded by small bubbles. It's just fluid going out of the layer here. And why is it so important? First, because in the ocean, it can greatly participate to sediment formation and transport. It is also crucial in terms of slope stability, or maybe I should say slope instability. Maybe, sorry, let me remove this. You can hear me better, sorry. It's also important in terms of offshore resources, because those guys here going up, the fluids coming from the seafloor, are often hydrocarbons. So when you observe them, it means they are the signature very often of deeper reservoirs. So it's very interesting to drill and get what's beneath. And finally, they are really important in terms of risk assessment. There are thousands of kilometers of optical fibers crossing the ocean. And when you find a region like this, you really don't know, and you would like to know if it's safe to cross this region or to make the round trip, which will cost a lot more money. And finally, you can think of the inverse problem. It's not natural fluid, but it's your own CO2 you want to trap in the seafloor, and maybe you don't want this situation to happen. So I show this picture, which is quite nice. It means that the diver is in a little jacuzzi, and it's quite sympathetic. But does it always happen like this? Is it always a gentle, natural fluid release? The answer is definitely no. And sometime in history, it has been documented some violent and very large-scale fluid release. Of course, in that case, you have no picture available. But there are many works about that. I don't quote all the works here. It is pointed out as a strong mechanism for global warming and climate change in history. I will give you three examples, three very important events which have been documented by geologists. The first one is a long time ago, 250 million years ago. We are not used to this kind of scale. It was nicknamed the Great Dying. Well, I won't make any explanation. And it was at the Permo-Triassic boundary. The second one was a bit closer to our living period, 180 million years ago in the early Jurassic. And the estimation is that it released about 27,000 gigatons of CO2. As a reference, I put here the anthropogenic release last year. It was about 34 gigatons. So we are still well behind what nature can do. It's still okay to try to reduce our CO2 emission, of course. And the last event, it's the closest to us that has been documented, was 55 million years ago. And it is called the PETM event, the Paleocene-Eocene temperature maximum. And the estimation was that the global Earth temperature rise of about 6 degrees. So it's really huge, and you can see it can have stronger consequences. So if now we focus on the phenomenon itself, what happens really at the seafloor, we go and have a look. There are three types of what we call focused fluid migration. What happens when the fluid is released? The first type is what is called a POC mark. It is characterized by pure fluid emission, and usually it corresponds to a depression at the seafloor surface. Here you have the bottom line is an example of seismic profile, vertical seismic profile through this structure. And you can see that we're talking about really large scale. I put the Eiffel Tower as a scale here. It's about 300 meters. And those guys here can go as deep as a few kilometers sometimes. Second type is a mud volcano. It corresponds to the release of fluid plus mud. And it is usually associated not with a depression, but with a positive bathymetry at the seafloor surface. And finally, there are injectite, which look a bit like the mud volcano, but they transport fluid plus sand, and they have a little bit different geometry. So you can see that it's crucial to understand the dynamics of this object because they are directly linked to the risk potential. And the problem is you can do as many seismic profiles as you want. They only provide a picture, a fixed picture of the present day state. You do not capture the dynamics of this system. And it is really important. I hope I convince you about that. So the first idea when you see that is, okay, I want to go and make maybe direct measurement. Let's go and have a look and maybe drill. We have the technology to go and drill on this system. It was tried in the past, and this is the result of the first and only attempt of direct sampling. So in the 1890s, a ship went there on a scientific cruise. It drilled and it hit a gas pocket, and the sea started bubbling around the ship, which merely sank. All the team was safe. Unfortunately, it sank quite slowly, so the guys could escape. But since that time, if you write a scientific proposal saying, I want to drill on that kind of structure, you get a 100% chance to get rejected. So direct sampling and measurements are really not possible. So what remains? Modeling. So basically what we want to model is a fluid rising through sediment leading to a particle entrainment. And our approach consists in a laboratory experiment of a fluid rise in particle-laden fluids. We generate a suspension here, and we inject through a single point, and the fluid can be either gas or liquid. Today I will only talk about liquid injection, that is to say two-phase systems, not three-phase systems. So this is a first experimental setup. It's what we call a Healy-Shaw cell. For those who are not familiar with that, it's simply two glass plates about 30 centimeter wide, 30 centimeter high, and they are separated by a thin gap about 2 millimeters. So it's a quasi two-dimensional problem. The good point is you can directly visualize all the phenomena happening in the system. We fill the cell by a layer of grains. It's typically spherical glass beads of about 100 to 200 micron diameter. And we immersed all the grains underwater. Then at time t equals 0, we open the valve here, and we inject water, so two-phase system once again, at a constant flow rate. And here is a little movie which I will play in a moment. So you have the initial condition, the grains here, the water layer on the top. It appears a bit dark because we put a blue dye to distinguish the initial water layer from the incoming water from the nozzle. And you all learned probably that usually when you inject fluid into a granular matrix, if you inject at slow velocity, you will have percolation. The grains will roughly do not move. If you inject very quickly, you will have fluidization. So what do we have here? That's what I love about physics. It's always surprise you. So, sorry. Oh, I made a spoiler, sorry. Ouch. So, okay, you have the transient state. You have a particle-laden jet, which forms. And let's forget about the transient today. And after some time, it stabilizes in a kind of stationary regime where the jet starts flapping left and right and left and right. And it's very regular. You can run the experiment for minutes or even maybe hours, and it's really, really regular. So in that case, we have a new regime that we didn't know before. It's a fluidization with oscillations. We can plot a regime diagram where here... Yeah, of course.
What was the minimum fluidization velocity for that? Right?
The minimum? Yeah. Sorry?
Minimum fluidization velocity.
For that specific experiment?
For this.
Maybe you can read in the regime diagram. I don't know if that answers your question. Okay, so if here you report the initial height of the granular layer. in that axis the injection flow rate, and you do recover your percolation regime. We didn't explore further up because it's already known. The fluidization regime, and inside the fluidization region, you have those oscillations appearing. What's interesting is that if you completely remove the particles from the system, so you are here, you always have a stable jet. So only the pure fluid mechanics system does not display this oscillation in this geometrical configuration. So let's have a closer look at the particle-laden jet oscillations. So here you have snapshots on the top line corresponding to one cycle of oscillation. And we can plot to visualize better the two spatio-temporal diagrams. So first we plot a horizontal line here in white. And you report the intensity of this horizontal line as a function of time. And you can see those very regular horizontal oscillations. You can do the same on the vertical line, which is at the vertical of the injection point. And you can see those vertical jet oscillations, which do not have the same frequency. So you can pick from these diagrams the horizontal jet oscillation frequency and the vertical jet oscillation frequency, Fx and Fz. And if you plot the vertical oscillation frequency as a function of the horizontal oscillation frequency, you can see this very clear linear relation with a slope 2. Slope 2 means, if you think a bit about the problem, that it's exactly analog to a solid body oscillation. So you have this kind of problem. And the frequency decreases when you increase the flow rate, that is to say, when you go from dark blue to yellow. Because the two frequencies are directly related, in the following I will only talk about the horizontal oscillation frequency. You can plot this frequency as a function of the opening angle of the crater, which is on the top right. I'm too small to point at it. And you find that they are also correlated. And finally, if you plot once again this frequency as a function of the flow rate, normalized by the critical flow rate above which those oscillations appear, you can see that all the data roughly collapse on an exponential decay. And after this exponential decay, you have a plateau. And this plateau appears when the angle theta of the crater reaches the average angle, which is about 28 degrees in our configuration. So I told you it's analog to a solid body oscillation. So let's go a bit further and see if it works. So in addition to measuring the frequency, we can also measure the oscillation amplitude, okay? And we can do this very simple model of a solid rod acting as a metronome. This is a model here. You just do a very simple geometrical calculation, and you can relate the horizontal oscillation amplitude to the vertical oscillation amplitude here, and Pz here is the temporal average of the maximum height of your solid object. And if you plot this estimation to the experimental measurement, of course it's scattered, but we are actually quite happy, because if you look at the scale, it's exactly the right order of magnitude. So the solid body, the oscillation model, which we call the metronome model, actually doesn't work so bad. And finally, if we plot the vertical oscillation amplitude as a function of the normalized flow rate, you see that you can fit these curves by empirical law with an exponent xi here, which depends on the initial granular layer height. And this law makes possible, by knowing all the parameters of the system, to predict the oscillation jet amplitude. If we want to tell the story in terms of dimensionless parameter, we introduce two dimensionless parameters. The first one is a Strual number. Basically, it's just a dimensionless frequency. And to make it dimensionless, we multiply by a characteristic length, which is simply the initial height of the granular layer. And we divide by a characteristic velocity, which is the jet velocity at the injector exit. The second dimensionless number, we called it J, so I really apologize to all the people talking about mu rheology as a function of J. It's not the same J here. This parameter was adapted from a classical parameter in hydrology and soil research, which is called the erosion parameter, which is usually defined for submerged impinging jets. And it corresponds roughly to the ratio between the impinging jet force to the particle resistive force. And it can be written as a function of the injection flow rate, the cell gap, the initial granular layer height, the jet angle, the opening fluid jet angle, and U, which corresponds here to the inertial particle velocity corrected by buoyancy effects. If we I'm sorry?
E?
E is a gap of the cell. So the distance between the two glass plates in the experiment. It's a confined experiment. So if you plot the Strahl number as a function of this parameter J, you find that all the data collapse on a power law with a slope minus 5/2. Now we would like to interpret the origin of the emergence of this jet self-sustained oscillation. Actually, if you do some bibliography, you found that there is a lot of work on the emergence of self-sustained oscillations, in fluid mechanics. So only with the fluids, not with grains. And there are two main theories to explain the appearance of oscillation. The first theory is a hydrodynamic origin. It says that when you have a jet in certain configuration, you can have a structure which are advected by the jet. They come back advected by a recirculation flow, and they interact with a nozzle. And this leads to oscillation. But in that case, the theory and also experimental observation predict that the Strahl number should increase with the jet velocity. J here is a direct function of the jet velocity. So it's not what we observe. Second theory is it can be of acoustic origin. So basically, it's the same kind of feedback loop mechanism. You have the generation of acoustic wave, but the jet, they can propagate upstream and interact back with the nozzle and generate oscillation. In that case, once again, there's a whole theory written about that, and you should find at low Mach number, which is definitely the case in our experiment, that the Strahl number is constant. Once again, it's not the case. So in our case, we really need coupling between fluid and grains, and that's how we interpret our observation. We do not have a theory at that point. If somebody has any idea about that, it's much welcome. I will quickly come back to the initial motivation, which is fluid seepage at the seafloor. Sometimes those kind of oscillations are observed in the nature. I took here the example of the Akon Mosby mud volcano, which is located up there in the very north of Norway, in the Barents Sea, and people have measured periodic fluid pulses, which are accompanied by eruption of this volcano. So you can see existence of this oscillation. It's qualitatively analog to what we observe in our experiment. I won't go further, but we are really willing to try making a link between those observations. I will now skip to the second part, which is soil erodability. Maybe you will ask yourself what's the link between the two parts. And actually, we don't study directly soil erodability, but we use a test case for soil erodability. And as a physicist, this test case was really great because it's a mirror image of our previous experiment. So you have exactly the same cell, same layer of grains immersed in water, but instead of injecting the fluid from below, you inject the fluid from above. So you have a jet impingement on a granular free surface. We also use spherical glass beads, and the varying parameter are the flow rate and also the impingement height. This is examples of, the first line is a snapshot of experiments at a different flow rate for a fixed impingement height. Typically here it's 3 centimeters. And the bottom line is just an example where we superimpose all the images from the same experiment, which gives an idea of the flow lines here. We put tracers here in the fluid. That's why you have all these tiny particles. They help us compute the particle image velocimetry, velocity field, and so on. So what happens for small injected flow rate? You have either no erosion or very weak erosion. You can see that nothing happens in the surface. When you start increasing the flow rate, you start forming a crater here. This is what I call an open crater. Open because the streamline recirculates, and you have those two vortices here, which are outside the crater. And then, if you continue increasing the flow rate, you form what we call a closed crater. Closed meaning that the crater has two little dunes on each side, which, overhang on the crater. Okay, you can see them here. So this is what we call a closed crater, and I will show you what happened, what's the dynamics inside the closed crater. Just a moment. Okay, so this is initial condition. You can see the nozzle here, the granular layer, all these tiny tracers here. And if I run the movie, okay, the jet starts impacting. You dig a crater, and look what happens in the crater. If you have good eyes, you should see that there are two vortices, and they start dancing with each other. Very regularly, actually. Okay, it's a loop, so I can let it play once again. And you can see, once again, oscillations happening inside this crater. Okay. Oh. Sorry. Okay, let's go back to the presentation. So once again, we can plot a regime diagram. This time here, as we consider the impingement height as a function of the injected flow rate. And you can see the regions where there are no craters. The jet is stationary. The region here with the triangles where there is a crater, but the crater is open and the jet is also stationary. And finally, you can see a whole region where the jet is non-stationary, which corresponds to the closed crater. Here, I only say that the jet is non-stationary, and I don't say there are oscillations, because they are not always oscillations. The dynamic is a bit more rich than in the previous experiment, and I will show you some examples of the different flow regime. So when here I have to define Q1 and Q2. You have the little picture on the top right, so you have the incoming flux, which is downward in black. And then if everything is symmetric in your system, you should have, by mass conservation, Q1 on one side, which is half the incoming flux, and Q2 on the other side, which is half of the incoming flux. The incoming flux here is represented by the dashed line, and you can see that in the symmetric case, here, Q1 equals Q2 equal half the incoming jet. No surprise. But you can also have, in some cases, an asymmetric jet, which locks on one side and stays for a long time on that side. You can have intermittent behavior, where the jet starts being symmetric with some fluctuation, and then suddenly will lock on one side and maybe start oscillating again and locks on the other side or on the same side and so on. And finally, you can have the case, which I show you on the movie, of quasi-periodic oscillations. We can define an asymmetry parameter, Xi, which corresponds to the temporal average of Q1 over the temporal average of Q1 plus Q2. And you can plot this parameter Xi, which basically varies between 0 and 1, as a function of, once again, this J parameter, which is exactly defined as in the previous experiment. And you can see that there is a region without crater, so nothing really exciting happens. Then, when you start digging a crater, the jet is symmetric here. And then you can have this very rich behavior where you can go from no oscillation and the jet is locked either on one side or on the other side. And when you move to the central line, you start having this very regular oscillation. Here the color scale is the probability of the jet to be in a given state, given by the dots. Once again, we want to make the story dimensionless. So we plot the Strual number, which is defined this time with the characteristic length, which is the impingement length, the height at which you inject the fluid. And the velocity, as in the previous case, it's the jet velocity at the injector outlet. You plot that as a function of the J parameter, and you find, once again, a beautiful power law, but with a slope, a bit different slope, which is -1 in that case. So thanks to this power law, which collapses all the data, you can predict the oscillation frequency as a function of all the experimental parameters. And what we did is we plot a nice spatiotemporal diagram. So you just cross the crater with a horizontal line and plot the intensity along this line here as a function of time. And you can see clearly the oscillation here with the gray shades. You can report on this graph Q1 here in orange and Q2, where you see the oscillation. They are a bit less smooth than in the previous case, but they do exist. And finally, you can also report on this graph the predicted frequency from this formula, which works quite well. And once again, we interpret this behavior as a coupling between the fluids and the grains. So now I will skip to the conclusions about the emergence of oscillations during fluid injection in water-saturated sands. I show you two experiments. The first one where we inject from below. We observe oscillation of the particle-laden jet, and once again, it's interesting to note that there are no oscillations without particles. We can interpret that as an analog to a solid body oscillation. It's a simple metronome model, which works quite well. And finally, we find this power law for the Schwall number as a function of the J parameter, which is reported here with an exponent -5/2. For the other experiment, you impact from above. You also observe oscillations in the crater. Once again, I forgot to tell, if you remove the particles, there are no oscillation. If you just impact the jet on a solid wall, horizontal, oscillation do not appear in our experiment. The dynamics is more rich. There are different flow regimes, stationary, asymmetric, intermittent, oscillatory, and so on. And the Schwall number also follows this power law, but with a different exponent. We still don't know how to explain the value of this exponent, but we feel that it comes from the coupling between fluid and grains. And if I have 2 minutes left, I want to show you the perspectives of this work. The first one is to move from 2-phase flow to 3-phase flow. Actually, historically, I started my work as a young researcher on this system, and they give very beautiful images, but when you try to go deeper into the physics, you find that it's hell because there are multiple bubbles, there are suspension heterogeneities, particle sedimentation, and so on. So you have an interesting dynamics, and it's very difficult to interpret. So recently, with a colleague from ENS Lyon, from my lab, and another colleague from LMFA in Lyon also, we moved to a very fundamental problem. We said, okay, we are physicists, let's simplify the problem, and let's study one single bubble inside a homogeneous suspension with density match particles. You would feel that this problem will give you simple observation, and you can interpret them. But even with that simple problem, we find very puzzling dynamics, which I can tell you around coffee, but it's not so simple. And the second perspective is I try to convince you since the beginning that we could model geophysical problems by a single layer of grains. But actually, when you look at the seismic profiles like this, there are many different strata in the sedimentary basins, and it looks like more like a geological millefeuille, and it's a bit of an illusion to say, okay, I will take one monolayer and I will understand everything. So the next step, okay, we are physicists, so we will move from one layer to 2 layers. It's a start. And the first idea is to study what happens at the interface. There are many interfacial phenomena. Here you have an example, I will show you the movie, of one layer of coarse grains, and the second layer on the top of finer grains. And you inject the fluid from that point, and please pay attention of what happens at the interface. And all physicists in the assembly will love that. So you see this very nice front destabilization before fluidization. Then, if you're a bit curious, you can run this experiment for some time. You can see this positive, what we call bathymetry on the top. And then you can consider, and this is my last movie, what happens when this kind of structure will die. That is to say, you just close the valve. So this is the kind of image you have in the stationary regime. And then you just turn off the valve. And you see this quite intriguing segregation pattern, where in the bottom layer, the grains are perfectly sorted, with the coarse grain in the middle, the fine grains completely on the side, and on the top layer, they are perfectly mixed. So there are still many open questions, and we have a lot of work to do. Okay, thank you for your attention.
Thank you, beautiful talk.
Thank you.
When you had the injection from below and you formed this crater and then you saw this bistable oscillation, that reminded me of the bistable Coanda jet that people use sometimes in aeronautical applications. Do you think there's any relationship there?
Oh, that's a good question. Can you remind me? I will answer with another question. Can you remind me the mechanism at the origin of the Coanda jet?
So the Coanda jet is when you have a jet coming out of a diverging nozzle,
Yeah.
the jet tends to attach itself to one of the side walls.
Yes, okay. Yeah,
and
yeah,
then when you perturb it in a suitable way, you can make it go back and forth.
Yeah, okay, I remember. It's a geometry-driven jet. I don't know. Actually, the experiment we wanted to do and we didn't perform yet was to make a solid crater profile. You can do that with a 3D printer and see what happens if you inject the jet in that solid crater. I don't have the answer yet.
Okay, thank you.
Okay.
We have our first Zoom question. So Malgan, can you unmute yourself online? We'll try and have you ask the question directly.
Hi. Hello, Valérie.
Hello.
Can you hear me?
Yeah,
Yes.
I can hear you perfectly.
It was a relatively simple question, but I was just wondering if something you didn't indicate is that how you might be changing regime as you increase the flow rate in your experiment when you get to oscillation. Like you didn't mention anything about like things like particularly Reynolds number and Stokes number, just to have an idea what are those when you kind of keep increasing the flow in that experiment.
Sorry, I'm not sure I got your question. Your question is how I change the J parameter? Is it correct?
No, when you increase the flow rate of the jet, and I was just wondering, like, what would be the Reynolds, the particulate Reynolds number? Is it getting like? I'm just wondering if it's the order 0.1 or is it getting around 100? Like, what is the range of when you increase Q of Reynolds number and Stokes number? If that could be anything important in that system.
Right. From my memory, I don't have the value here because we made our reasonment based on the J number. But from my memory, we calculated a couple of times and it was always above 1. I don't know if that answers the question. You're welcome. I can make the computation again and tell you more.
Cool. So eventually it goes from 1 to 10 or something.
Maybe.
As you increase Q. Interesting.
Yeah,
well, thank you.
I have the value in mind. Sorry.
Thank you.
We've done similar kinds of experiments numerically, and we found a third regime between the percolation and the full fluidization. And basically, a pocket opens up in the middle, and percolation, you see, get kind of an open space, and then percolation happens through that. There isn't enough energy to fully fluidize, but it's enough for it to kind of open up a little manifold inside. That fluid collects it, and then goes through percolation.
Yeah. Actually, in some experiment, I didn't show here, but we do observe in the transient regime the formation of a cavity, which is really similar to what you mentioned. And after that, the cavity disappears because somehow you manage to fluidize at a longer times. Yeah. Mm-hmm.
Really nice talk. Thanks.
Thank you.
I am very interested in, but I noticed the segregation pattern that you pointed out at the end. It looks, can you show that? Okay.
Oh, yeah.
Run it and then, and I'll ask my question as you run it. The large particles look like very quickly they settled into this sort of V-shaped segregation pattern. Is that right?
Yeah.
Do you have any sense for what's going on there?
You mean why the fines are here and why the coarse particles are there?
Yeah. Do you have a sense? So folks have done some research on like the importance of sort of circulation patterns in sort of advection plus sort of the preferential segregation drift. And then
Now, actually, I don't have a clear explanation, but maybe I can have a hint. I guess that particles are entrained vertically, and then there are two recirculation rolls inside, if you focus on what's happening in the fluidization region. And the coarse grains are heavier. So in this recirculation loop, they will fall closer to this axis, and the fines will be entrained quite far. Actually, we did experiment before with a monolayer, and we found at the beginning we were not very clean in doing the experiment, so the grains had a lot of dust inside, and we didn't pay attention. And we found that when you form a fluidized region in a monolayer, not in a bilayer like this, we always had a black line marking the boundaries of the fluidized region. And it took us a long time to understand what was that black line. It was quite convenient for image analysis because you could pick immediately the size of the fluidized region. And then we found it was a dust particle, a tiny dust particle, which were sorted completely on the sides. And after reading some bibliography, we found that it's exactly what happens in kimberlite, how do you say that? In kimberlite formation, which is a kind of volcanic clastic events, very violent, whereas geologists find that the coarse grains are on the center, and you find these fine grains in the side.
Thank you.
You're welcome. Yep.
If you moved out of a Healy-Shaw geometry, so you had a three-dimensional system,
Yeah.
do you still get these oscillating jets?
I don't know. I don't know, and mostly because here everything is plotted as a function of the J parameter, and you pointed out rightly that E, the width of the helical cell, appears in the system. So I really want to move to 3D to check if you do have that, or if it's only a confinement effect. So somehow you need a confinement to generate the oscillation. I don't have the answer.
Just a quick question. In your single phase grain,
Yep.
the earlier part of the, what is the grain size? 200 micron?
The grain size is it's a polydispersed batch ranging from 106 to 212 microns, and it's quite a wide dispersion.
Just a suggestion. I think if we want to understand what caused that interaction, especially oscillating jets, you might just want to do 200 micron, 400 micron to see, because there could be those numbers.
I fully agree. So we could do that. We could achieve that by sieving. The only problem is we are a bit limited in the size of the particle. You cannot really go above 300 or 400 microns because the cell gap is 2 millimeters. So after that, you have very few particles in the gap, and you can have like clogging or this kind of things. So at the end, you're a bit limited somehow between 50 microns and 200 or 300 microns. But it's already something, and definitely we have to try. Oh. Mm-hmm.
Nice talk. Thank you.
Thank you.
So, if this is a Healy-Shaw cell, is it narrow enough that the flow is in the Darcy regime, in the fluid flow is through the medium, is like a Darcy flow? In the sense that the pressure drop is proportional to the velocity? The reason I ask is, so when you have that crater forming there,
Yeah.
I mean the triangular region, is the fluid permeability through the material important, or once it just forms, the fluid just flows straight up?
The fluid, the permeability is important. This I can answer for sure, because in some experiments, you can see the percolation pattern still growing inside the grain matrix, the one which remains still on the sides. So you also have a fluid circulation in the granular matrix.
So
yes.
If you had a boundary that was rigid, you would not see those oscillations like I was asked before?
I don't know. It was one of the questions. I'm not sure, because maybe it's only the crater geometry, the coupling between the jet and the crater geometry, which creates the oscillation.
Okay.
So
thanks.
It's not so clear.
I'll take one final question at the back.
Yes. No. Oh, sorry. I hear you, but just a little. Yeah.
Going back to the two-grain experiment, beautiful, the depth, the end of the experiment. So I expect to have gravitational sorting. So the fine particles should, if you do really high resolution analysis once you stop the jet, do you see that the dark particles arrive to their location after the bright particles? So is it...
You mean in that region?
No, on the boundary.
On the bottom. Ooh. Let's watch the movie again. It's like they're always there. Even when the experiment is running. So I don't know, this experiment I haven't looked, but in the other experiment I was talking about, the monolayer with dirty grains, where we show this very fine dust on the side. At some point we were curious, so we make a zoom on that side, and it's a kind of, I don't know if I'm authorized to call that a creep, but this very thin layer, Douglas will tell me, yeah, we're in the creepy session, so I have to justify somehow. But you can see that it's moving very slowly. It's really moving very slowly, but it's there, even when the experiment is running. So from what I see from this movie, of course, there is no zoom, so it's a bit difficult to assess, but they are always there. Yeah.
Thanks, Valérie.
Thank you very much.